Well, when we're examining functions of several variables, it would be useful to know that they behave in nice ways. For instance, the sum of two such functions, or one function plus another, will behave in a linear fashion. So f plus g of xy is the same as f of xy plus g of xy, and the same story with minus, and the same story with times, and the same story with divide, with a possible exception. Now, in other words, f over g of xy is f of xy divided by g of xy, as long as g of xy is not 0. And function composition also works the same way. So f of g of xy is, or f composed with g of xy is f of g of xy. So that's kind of good news. Functions of multiple variables behave the way we expect them to. Here's another problem with domain and range and a sketch. Domain and range and a sketch. So we'd like to know the domain of f of xy equals the square root of 16 minus 4x squared minus y squared. Well, first of all, whatever x is and whatever y is, these are going to be subtracted from 16. And so if x and y are the smallest possible values, then they would be 0. Because if they're negative, you square it and you get something positive. And then we'd be subtracting something from 16. So the largest value for the range of this is square root of 16, which is 4. And the smallest value for the range would be wherever 4x squared plus y squared is equal to 16. Because they couldn't be greater than 16, because then you have a imaginary square root of a negative, and that's not allowed. So the range is numbers between 0 and 4. Since 4x squared plus y squared has to be less than or equal to 16, so the domain is the inside and boundary of this ellipse. By the way, to get from here to here, all you have to do is divide both sides of the equation by 16, and if you do that, you should see, oh yes, it is this ellipse with major axis length 8, minor axis length 4. That 8 comes from 2 times the square root of 16. And it's stretched up in the y direction more than the x, so that's the domain of this function, is points on that ellipse. And so give a sketch of it. Well, if f of x, y equals 0 is on the boundary and is largest when x and y are 0 at 4, so I already talked about that, so never mind. I didn't mean to say that again. So the graph is just the top half of this ellipsoid. By the way, if you make z equal to the square root of x 16 minus 4x squared minus y squared and square both sides, you get z squared equals 16 minus 4x squared minus y squared, or 4x squared plus y squared plus z squared equals 16. And so you get this ellipsoid if you divide both sides of that by 16. Recall that's one of the quadric surfaces. And x-axis intercepts are at plus or minus 2, y-axis intercepts are at plus or minus 4, z-axis intercepts are also at plus or minus 4. And I really struggled to get MathCAD to draw this function. Actually, I couldn't. But I did want you to see the picture of it and explain a little bit about the domain. So I had to cheat and go to spherical coordinates. So bear with me as I go into spherical coordinates. We say x of phi theta is 2 sine of phi cosine theta. Oh, anyway, you can see that, and you can believe that, but I did get it to draw it. Now, here's the thing. The range is from 0 to 4, so if I turn this on its side, then you only should be looking at what is above, well, what's in between here, 0, and here. So it's only the upper half of this ellipsoid. Funny looking ellipsoid, isn't it? Looks like a a one-a-day vitamin pill or something like that. Oh, if I made it all red, then it would look like a one-a-day vitamin pill. But keeping in mind, though, that it's only from here up, right? So I captured it and dulled it up a little bit. And it's just the top part, just this part right here. And notice, if you look, here is that ellipse. To recall, the ellipse that was the domain was these points and the points on the boundary as well. So points inside that ellipse and points on the boundary of that ellipse is the domain. I think that actually shows up in this picture, that the ellipse is just those points inside that ellipse and on the border. So for what it's worth, each of the horizontal stripes in the above picture is a trace of the graph in a plane parallel to the XY plane. In other words, this one is in maybe the z equals 1/2, and this little line here is z equals 1, and maybe this one would be where z equals 2. And these are called the level curves of the surface. See why they're called level curves? At level 2, we have this intersection of the plane z equals 2 of the surface, so they're called level curves. And so another way to visualize a function of two variables is to examine its level curves. You know, these are hard to visualize. I'm fortunate that I have some software that'll let me do that. If I was teaching this class face-to-face and trying to draw these things on the blackboard, it could be very challenging. You can find this by letting z take certain values and graphing z equals f of xy and r squared. You should be familiar with contour maps giving elevation, and weather channel showing maps of temperature called isotherms, or pressure isobars. Another use of this is in electricity, where electrical potential fields are represented with equipotential lines. But I'll leave that for your physics teacher. The level curves for the above ellipsoid, since I'm continuing with that example, are shown in this picture. Here I got the graph of it. And then I drew level curves at z equals 0, that would be in the xy plane, z equals 1, of course that would just be our ellipse, z equals 1, z equals 2, z equals 3, and z equals 4 is there too, but it's just a point at the very top, and it isn't shown by the software. So again, I had to go to spherical coordinates for you to see this, and so bear with me as I am there in spherical coordinates. And the level curves, also, again, don't forget, it's only from this point up, right? But I can't get both of these to draw at the same time. And here's another problem. These level curves are drawn in the plane, looks like z equals -4. They should be in the plane z equals 0, but my software wouldn't do that. So, well, I don't think they will. I don't think it will. But maybe I shouldn't give up on that thought. Yeah, I think I'll give up on that thought. But these are the level curves. At the very bottom would be the point that was going to be up here. This curve on the outside would be when z equals 0, and then when z equals 1, 2, 3, and 4 are the curves that are inside. So those are the level curves for this. So here's another example. Can we sketch the level curves for the function in example 1? That was this one. And yeah, you do so by letting f of xy take on different numbers, 0 possibly. Of course, then it would only be a point, because x squared plus y squared over 4 equals 0 has only one solution, x and y are both 0. But if we put a 1 in there, then we got x squared plus y squared equals 4, and that's a circle with center at the origin and radius 2. And so I hope you can see the level curves for that paraboloid, and the level curves are, and this one fortunately is actually drawing the level curves in the xy plane like it's supposed to. So there's the function itself, x squared plus y squared over 4, or f of xy equals x squared plus y squared over 4. And there are its level curves. Of course, they just keep going on, concentric circles.